Okay, g'day all and welcome to another video. So today we're going to be talking about the flags register. So the flags register is another register inside the computer. It's not general purpose, so we can't use it for things like arithmetic. But it's used for things like comparisons so that we can branch. The flags register was originally just called flags and it was 16 bits wide, but then in about the 386 days it was increased to 32 bits wide and we got the E-flags register. And nowadays in 64 bits, we've got this 64-bit flags register, and some are for system programming, some are for general purpose programming, but most of the 64 bits in the flags register are not used at all. Okay, so today I just wanted to go through some of the most useful or the most important bits in the flags register. And a lot of what we're going to be talking about today is not really useful until we learn things like the conditional jumps or the conditional moves and the set byte. Those sorts of instructions, but yeah, today I just thought we'd have a bit of a talk about the flags themselves, and later on we can go through the instructions that actually use the flags register. Okay, so the first bit that I want to talk about is bit number 0. This is called the carry flag. Now the carry flag is set to 1 whenever there's an overflow, and in Visual Studio it's called CY. So if I can just get my... Well, first of all, We'll talk about what it does. So the carry flag will be set to 1 whenever there's an overflow on the left-hand side. So if we've got a number, say mov rax -1, for example, rax, let me just zoom in a bit. Rax is going to be filled up with 1s, and if we add 1 to that, what we're going to get there is an overflow. So the carry flag is an unsigned overflow on the left-hand side. So whenever your register can't hold any more and it wraps back around to 0, you should get the carry flag set. If I just put a breakpoint there on that line and we hit run, we should be able to see the carry flag point. Okay, so we've broken in our program. If you want to open up the registers window, you go up to debug, and in Windows, you come down here to registers and you just click on that. So this will usually be docked up the top here, tabbed, I think, but yeah, at the moment it's not. The other thing, if you can't see the flags, these are the flags just here. If you can't see the flags, then you want to right click and come down to flags and just check that. Yeah, okay, so the carry flag is CY over here in Visual Studio. Now, I don't know why, but Microsoft calls the flags different abbreviations, so they don't use the normal abbreviations. We'll go through what the different flags are in Microsoft Visual Studio as we go. So CY is the carry flag. At the moment it's set to 0. If we run past that next line, that mov instruction, the flag is still set to 0, but right here we should get this overflow, this carry. Yeah, there you go. So the carry flag was set to 1. So all that it's saying is that there was an overflow on the leftmost bit. Yeah, so if this was another number, say this is a byte, we might be AL and we might be 255, and we might be add AL and 1. Okay, so the byte AL can't hold more than 255. So if we add 1 to 255 in a byte, then we'll also get that same overflow. Okay, the next flag that we're going to talk about is called the parity flag. Okay, the parity flag is bit number 2 in the flags register, and it's not really useful. So the parity flag comes about from, I think, back when we used to use other methods of transporting data around, and it was important that you know, for the integrity of the data, that people could send, say, 7 bits worth of data, or just the low 7 bits of a byte, and then they could send the parity bit as well to indicate whether there was a odd or an even number of 1 bits in the data that they sent. And that means that if you ended up with a parity bit that didn't match the rest of the 7 bits that you were sent, you could tell that there was an error in the transmission somewhere. It's set to 1 whenever parity is even. So the parity is the number of 1 bits in the result. The parity flag in x64 actually only counts the 1 bits in the lowest byte of the result. So if we've got something like, I don't know, maybe mov EAX and 3. So the value 3 in binary is 1, 1, which means that if we perform some operation on this, maybe AND EAX and EAX. Okay, so the result of ANDing 3 with 3, the result is just 3 again. So 3 has an even number of 1 bits. It's 1, 1 in binary, that's 2. 2 is an even number. So what we should get when we run this is an even parity, or the parity bit set to 1. What I might do also is after we've done the even parity, we'll do mov EAX and 7, and we'll check some check odd parity. Okay, so I'll hit run. PE is the parity flag. Yeah, PE for parity even, I think. Okay, so after the mov and the first and there, PE is 1 to mean that there was an even number of 1 bits in the lowest byte of the result. If we go down to the next and down here, you'll see that PE is 0, or in other words, the parity was odd. It wasn't even. Yeah, since there's an odd number of 1 bits in the result. Okay, so I just want to mention again that parity is not really used nowadays. Nowadays we have different methods of maintaining the robustness of our data. But it was originally used for just making sure that data transmitted correctly. I think when you're dealing with serial data transmission more than anything. But nowadays we don't tend to use the parity flag at all, really. Yeah, it's just there for backwards compatibility. Okay, so the auxiliary carry flag is the next flag that we're going to talk about. The auxiliary carry flag is bit number 4, and just like the parity flag, nowadays we have this due to backwards compatibility, and it's not particularly useful. So bit number 4 is the auxiliary carry flag, and it indicates an overflow on the lowest nibble of the result. So bytes are 8 bits wide, a nibble is 4 bits wide. So if there's an overflow on the low 4 bits of your result, then you'll get the auxiliary carry flag set to true. So how would we demonstrate this? I think if we mov into EAX 15, yeah, 15 is 1, 1, 1, 1 in binary. So that's all 4 1-bit set in the lowest nibble. And then if we add 1 to that, what we'll get is an overflow on that low 4 bits. So we should get the auxiliary carry flag set to 1. AC is the auxiliary carry flag in Visual Studio. Okay, so after the first mov, AC is 0. And after the add just there, it overflowed. Yeah, so the auxiliary carry gets set to 1. So it might seem a little pointless to have this carry flag for the lowest nibble of your result. But what it was originally for was this binary coded decimal, or BCD, instructions where the CPU would try to do, or wouldn't try, it would do a bunch of decimal arithmetic operations. But nowadays, binary coded decimal in 64-bit has been completely removed. So you can't do the binary coded decimal instructions anymore unless you're in 32 bits. Okay, so it's just for backwards compatibility, really. And we don't tend to use the auxiliary carry flag or the parity flag anymore. Okay, now bit number 6. Bit number 6 is very, very useful. Bit number 6 is the 0 flag. What I want to say is that when we talk about the way that the flags are set with instructions, it's only generally the case. And really, to know exactly how the flags are going to be set, you just need to read the instruction reference manuals from Intel or AMD. Things like the MOV instruction won't set the flags at all. And there's a lot of other nuances as well. So things like INC and DEEC, they don't set the carry flag. So in order to know exactly how instructions will change the flags, you just have to read the reference manual. Yeah, there's a lot of little strange things in there. But anyway, bit number 6, the 0 flag. So whenever the result is 0, if we do something like, well, this is a very good example actually, EAX, EAX. Okay, so that's a common way that assembly programmers zero a register, just XOR it with itself. That would cause the 0 flag to be set to 1 because the result's going to be 0. The other thing that we could do maybe like add EAX and 5. That would cause the 0 flag to become 0 because the result of adding 5 to 0 is obviously non-zero. So let's have a bit of a run and we'll see what we get. Okay, so after the first instruction, a ZR is the 0 flag in Visual Studio. So ZR at the moment is set to 0. If we run this little XOR instruction just here, ZR becomes 1 because the result in EAX just here, this first operand, was 0. And if we run the next instruction, add 5 to that, then the 0 flag gets set back to 0. Okay, so the 0 flag pretty much just tells you if the last result was 0 or not. And one of the reasons why that's really, really used, or very, very common, is the compare instruction, comp, actually performs a subtraction in the background. So if we do something like compare EAX and ECX, the compare instruction actually subtracts the value of the second operand, ECX in this example, from EAX, and it sets the flags as though it had performed that subtraction, but it doesn't set the result of the subtraction in EAX. Yeah, so normally if you performed a sub EAX and ECX, you'd get the result of that subtraction in EAX, the first operand. But compare does exactly the same thing, it just doesn't set the result. Yeah, so it sets the flags, but not the result. Which means that if ECX and EAX have the same value in them, then the result would be 0. Yeah, so say they both have 5 in them. 5 minus 5 is 0. So often for the 0 flag, we'll talk about equality, and we'll say JE for jump equal. Yeah, so some label. Yeah, so the 0 flag and being equal and not being equal, they're very, very closely related because of the way that the compare instruction performs a similar operation to subtraction. Anyway, the 0 flag, really basic stuff, just tells you if your result is 0. Okay, bit number 6 of the flags register is the sign flag. And the sign flag is really, really simple. All that it's going to tell you is whether your answer was negative or positive. So if the sign flag is a 1, then it means that the last result was negative, if you're reading it as a signed integer. And if the sign flag is 0, then it means that your last result was positive. Okay, so how do we demonstrate this? First of all, I'll just hit stop for a second. There we go. All right, so to demonstrate the sign flag, what we might do, well, let's just mov EAX and 7, and we'll mov ECX and 12. Okay, so if we subtract 12 from 7, we should get a negative number in EAX. Yeah, we'll add it again. Okay, so we've got 7, we'll subtract 12 and get a negative number, then we'll add 12 again and we'll get back our 7. So what we should see, this is really odd, but in Visual Studio the sign flag is called PL. So we'll see the sign flag gets set to 1 when the answer is negative, just here, and then it'll be set back to 0 when the answer is positive. So let's just step through and see what happens. Okay, so the first subtraction just here ends up with like negative 5 or something. Ends up with a 1 there because our result in EAX was negative. And then if we run the next instruction, our result was positive. Or 7. Positive 7. So PL, the sign flag, is set back to 0 to indicate that the result was positive. Super simple stuff, just indicates whether the last result was negative or positive. Okay, so bit number 10. Now bit number 10 is the direction flag. And I want to go through this in more detail when we talk about the string instructions, because that's really what it's for. It determines the direction of the string instructions. So the string instructions, what they do is they automatically increment or decrement a pointer so that you can read through a string of data in either a positive or a negative direction. If you're counting up through RAM, reading through a string 1 byte at a time going upwards in memory, then it's said to be reading the string positively or forwards. The other option is that you could be counting down in RAM. You could be reading the string backwards. So if the direction flag is set to 1, which is STD, we'll do that. It's an instruction to set the direction flag. Then you'll be counting negatively. Yeah, if the direction flag is 0, which is CLD, clear the direction flag. So your string instructions will be automatically incrementing the pointer upwards in RAM as they operate. Yeah, like I said, we'll talk more about the string instructions and the direction flag when we actually look at the string instructions. The other thing I want to mention about the direction flag is that it's UP in Visual Studio. So we might just do STD and CLD a few times. Yeah. The carry flag also has easy ways to set and clear it. There's STC, set the carry flag, which is set the carry flag to 1, or CLC, which will clear the carry flag to 0. Yeah, most of the flags you can't change that easily, but the direction flag and the carry flag have these special instructions for them. All right, but we can have a bit of a look at the direction flag. So I think UP in Visual Studio, I don't know why, I really don't, but set the direction flag. There you go, UP becomes 1. Clear the direction flag. There you go, it becomes 0. And set the direction flag again, it becomes 1. Yeah, once again, these only make sense when you're talking about string instructions. So we can have a bit of a look at how that flag actually changes the direction of the pointer when we're looking at string instructions. And bit number 11. Bit number 11 is the overflow flag. The overflow flag. Okay, so the overflow flag represents a signed overflow. It's like an overflow on the second from leftmost bit. So if you think about the carry flag tells you if there was an unsigned overflow. So for instance, if the byte 255 overflows to 0, then the carry flag will be set. But the overflow flag is a similar idea for a signed value. So if we've got something like... Okay, so here in the example of our overflow flag, what I'll do, I'll set AL to 255, which is the same as -1. It's every one bit, or every bit is set to 1. And then we'll shift that to the right, 1 space. And that'll mean that there's a 0 on the very left-hand side, but all of the rest of the bits are 1. And then we'll add 1 to that. So what we should get, first of all, is a negative number at the very start. If we're reading this as a signed value, 255 in a byte is the same as -1. Okay, so we got ourselves a negative number, and then when we shift right just here, we should get the overflow flag set because the negative value has changed to positive by that shift just there. And when we add 1 to that now positive value, what we should get is an overflow back to negative again. So the overflow flag should be set twice here. Yeah, it just means that the sign changed inexplicably. There was an overflow on the second from left bit, or a signed overflow. OV is the overflow flag. Okay, so at the moment, after the MOV instruction, the overflow flag is 0. Alright, so overflow flag at the moment is set to 0. If we run through the next instruction, this shift right, we overflowed, or the sign changed. And if we run through the next instruction, adding 1 to that, our sign changed again. Yeah, you can't really see. It's this 80 down here on the very left-hand side. Maybe we should try that again with RAX. Yeah, I might just try it again with RAX. Remove -1 since I don't know what the value would be. And 1. And add RAX and 1. I think you can use ink as well here. Ink. Yeah, so ink doesn't change the carry flag for reasons unknown. I think it's got something to do with the loop instruction. Ink doesn't change the carry flag, but it does change the overflow flag as far as I know. Let's hit run. No, there's a problem. Ink RAX1. Yes, it's not a very... sorry. Okay, so MOV RAX. Okay, so RAX at the moment's got a bunch of Fs in it, or it's all filled up with 1s from left to right in binary. If we do the shift, we set the overflow flag just there. If we do the ink, we set the overflow flag again. Yeah, so the overflow flag is set to 1 whenever there's a signed overflow or the sign of the result changed. Now, in a future video, when we come to look at the way that jumps are coded, we'll see that there's a lot of different types of jumps that we can do, that the CPU allows us to do, based on combinations of these flags. So checking if the result is negative or positive, or if the two operands were equal or whatever. There's also a whole bunch of instructions called the conditional move instructions that were added, I think, maybe Pentium days or something. It's quite an old instruction set nowadays. But it saves you a lot of time because it means that you can perform the equivalent of branching in the CPU without actually branching. And branching is really, really expensive, so CMOVs can save us a lot of time. Okay, there's also a bunch of conditional byte setting instructions that set the result to 0 or 1. Based on the flags register as well, so we can have a bit of a look at those too. There's a whole bunch of other flags like your trap flag and your interrupt flag. There's a flag for seeing if your CPU can perform CPU ID instruction, and all of these sorts of system flags. There's a whole bunch of different flags, but we're just covering the basic flags today, so we won't go through those. Okay, the final thing that I want to mention is how you actually change the flags register or read all of its bits. There's a couple of instructions used to push and pop the flags register from the stack. So pushfq in 64-bit days will push the entire 64-bit flags register. Then you can use pop RAX, for example, to pop the value into RAX. So at this point, RAX is going to contain the 64-bit rFlags register. And whoops. Then you can change it however you want. You can call push RAX and then pop FQ. to pop the value on the stack back into the flags register. So that's how you read each of the bits of the flags register. And that's just a little introduction to the useful flags, or to the general purpose programming flags of the flags register. And yeah, cheers for watching. Have a good one.